Hello everyone, this is the second part of the second lecture of the first week. And today, in this lecture, we're going to talk about the basic probability concepts, which is to say something about probability. The word probability itself is actually not well defined. There are actually three common interpretations. One is that all outcomes are equally likely, and this is the sort of traditional interpretation, since it's good for games, particularly games of chance, where a lot of probability theory originated in the gaming houses of Europe. The basic idea was to start off with the assumption that all of the possible outcomes were equally likely, and then build up probabilities on the basis of that. Another interpretation is just straightforward subjective interpretation. This requires experience, so you estimate probabilities just based on how often you've seen something happen in your experience. The problem with that subjective interpretation is that it's not so easy to quantify. So mostly in probability theory we use the last interpretation, which is the so-called frequency interpretation. And that's what we're going to use in this course. Basically, it's saying that the probability that event A takes place is the number of times that A occurs in a sequence of experiments divided by the total number of experiments or trials. And this now becomes a quantitative estimate of the probability of the event A. So let's illustrate this with an example. 2.5. What is the probability of drawing a king of spades from a deck of 52 cards? The basic approach is to first of all define the sample space and draw a Venn diagram if you can, assign probabilities to each possible outcome in the sample space, and then determine the probability of event of interest. So the Venn diagram for this particular problem is all 13 card numbers. I'm going to let ace be high, so it's 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, ace. And then we have 4 suits: spades, hearts, diamonds, clubs. So all together we've chopped this sample space up, and I forgot to put the S on this. So this is our sample space. Is chopped up into 52 equally sized blocks. We make them equally sized because we're going to assume that these events are equally likely. And that makes use of that first interpretation, equal likely outcomes. So we're assuming equal likely, so we can assign probabilities to each outcome. And so each of these blocks has probability 1 over 52. And so therefore, the probability of drawing a king of spades is just the probability of my dart landing in this block here, which has area or probability of 1 over 52. We could then ask, what is the probability of drawing a diamond? That basically is the event probability of a diamond, is the probability that I draw a 2 of diamonds, or a 3 of diamonds, or a 4 of diamonds, so on and so forth, up to an ace of diamonds. If these events are disjoint, then all I have to do is add up their areas. And so basically the question is, are these disjoint? In other words, if I drew a 2 of diamonds, could I also have drawn a 3 of diamonds? Well, no, I can't have. So therefore these events are disjoint. And that means then the probability of getting a diamond is just the area corresponding to 2 of diamonds plus 3 of diamonds, and so on and so forth up to the ace of diamonds. So it's basically the area of this row in the Venn diagram. And we know that row is 13 elements in length, divided by either each 1 over 52. So the total probability here is 13 over 52, which is 1/4. Well, there's 4 different suits, and we're just asking the probability of drawing one of the suits. The probability of drawing any of these suits is equal likely, so it's got to be 1/4. You can think of it that way as well. Next question might be, given that you have drawn a diamond, what is the probability that you draw another? The sample space now is more difficult to draw. In fact, I don't think we can, because we don't know which diamond was extracted. So I go back up to this picture up here. I know that one of these diamonds is missing, but I don't know which one. All I'm told is that I've drawn a diamond. So basically I know I've got 13 elements here, 13 elements here, but now I've only got 12 elements here and 13 elements here. So I can't exactly draw the sample space as I did before, but now I can divide the sample space up into 4 regions, one for spades, hearts, diamonds, clubs, and assign the probabilities. Again, assuming equal likely outcomes, the diamonds only have 12 elements, so the probability of hitting a diamond is 12 over 51. The rest of them are 13 over 51. So the probability of drawing another diamond is 12 over 51. And like I said, we could not answer the question, given that you had drawn a diamond, what's the probability of the next drawing the ace of diamonds? We couldn't ask this as a detailed question. If we don't know which diamond we've drawn, we don't know what the probability of drawing an ace of diamonds is. Because if I drew an ace of diamonds the first time around, the probability of drawing an ace of diamonds again is 0. If I knew that I drew a diamond that wasn't the ace of diamonds, then this probably becomes 12 over 51. So the answer to this question is either 0 or 12 over 51. Another example is the coin toss example, and we'll see quite a bit of this in the course of this course, because it's a simple way of viewing a sequence of discrete outcomes. Suppose a coin is tossed 3 times and the sequence of heads and tails recorded. The sample space S of all possible outcomes consists of 8 outcomes, S1 through S8. What are these outcomes? Let's first of all define our sample space. We could have had HHH, or we could have a tail followed by an HH, head, tail, head, head, tail, head, tail, tail, head, tail, tail, head, or tail, tail. And I'm going to assume that these are all equally likely to occur, so the probability of any one of them is 1 over the number of possibilities. So there's our sample space. Then we've defined some events here. If A is the event that at least one head is obtained on the 3 tosses, B is the event that a head is obtained on the 2nd toss, C is the event that a tail is obtained on the 3rd toss, and D is the event that no heads are obtained, enumerate the elements of these events and evaluate their probabilities. The last question is, what interpretation did you use in order to evaluate these probabilities? We've already answered that. We're assuming that these outcomes are all equally likely. So the first one, A, is at least one head is obtained on the 3 tosses. So if I look through, I got at least one head, at least one head, at least one head, at least one head, all the way down to here. So this A is going to consist of the elements S1 through S7. And I've written it this way. And the probability of A is then the probability that S1 occurs, or S2 occurs, or ... or S7 occurs. Again, we got a union, so we ask, are these disjoint? So if I got S1, could I also have got S2? Well, if I got HHH, I could not have got THH because I got HHH. So that means that these events are all disjoint, so I can just add up the probabilities associated with each of them. That's 1/8 plus 1/8 plus 1/8, 7 times. So the probability of this event A taking place is 7/8. What was B? B was the event that a head is obtained on the 2nd toss. So I go through here, I see there's a head on the 2nd toss, there's a head in the 2nd toss, here's another one, so S1, S2, S4, S6. So S1, S2, S4, S6 is what we should have. S1, S2, S4, S6, that's correct. Again, these are disjoint, so the probability of event B is just 1/8 plus 1/8 plus 1/8 plus 1/8, which is 4/8. C is the event that a tail is obtained on the 3rd toss. Let's see what that gives us. S1, S2, S3, S7. And I think that's it. So S1, S2, S3, S7. Let's see what we have down here. Did I read this wrong? S4, 5, 6, and 8. Oh, it's a tail. Okay, sorry. C is the event that a tail is obtained on the 3rd toss. So we see S4, S5, S6, and S8. Let's see if that's what we got. S4, S5, S6, and S8. And the probability then of C is the probability that I got this, or this, or this, or this. They're all equally likely and disjoint at equal 1/8 probability each, so I get 4/8 again for probability of C. Okay, let's look at D. D is the event that no heads are obtained. I think that's probably pretty clear. The only case that is S8. So D should be just S8, and the probability of this happening is just the probability of S8 happening, which is 1/8. By the way, we know that if it's a fair coin, the probability of getting in this case, a tail on each toss is a half. So basically, to get 3 tails in a row is going to be a half times a half times a half, and that gives us the 1/8 that we're looking at. Okay, and that concludes this part of the lecture.